Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss some analysis of results from MD simulations. There are many analysis that is possible for a given system, but we will focus on one particular property for a liquid structure and then calculation of time correlation functions. So, this workflow shows the various steps involved in MD simulations. So, in this MD simulation, first the most important thing is to generate the trajectories. Prior to the generation of trajectories, we have to decide what model system, what are the finite difference method that we want to use to integrate equations of motion. So, once we have decided those, then we can start the simulation with initialization, which involves assigning initial positions and initial velocities for all the particles in the system, ensuring that there is no overlap. And then we run a MD simulation for a period of time where the system reaches equilibrium. We looked at various means by which we can test whether the system has reached equilibrium or not. These includes looking at instantaneous values of potential energies, kinetic energy, temperature, pressure, etc. We can also check whether the system has stuck in a metastable state or not by giving a perturbation. We can also look at a mean square displacement to characterize whether the system has truly reached equilibrium or not. Once we have finalized that the system has reached equilibrium, from that point onwards, we extend the MD simulation for a little longer time, over which we try to measure certain properties, macroscopic properties in the simulations. So, the period of simulation in which we calculate the material properties are known as production runs. So, in this lecture, we will see how to measure certain properties in the production run. So, in the production run, what we do generally is we store certain information, microscopic variable information at certain period of time at equal intervals. Typically, for every 5th time step or 10th time step, we store the microscopic details. These microscopic details involve the positions, in the case of molecular system, even the orientations, velocities or angular velocities, forces, torques. So, these are some of the microscopic variable. We can write it in a file and store it as the simulation goes on. We need this information so as to process post-process to calculate certain properties. And when we try to record these positions, we may also choose to store positions which are either subjected to PBC or without also. The reason is that if you want to calculate mean square displacement, we are interested in the absolute positions without subjecting into periodic boundary conditions. So, in sometimes we have to store without PBC, in other times we may want to store with PBC. It all depends on what property we want to measure. So, now all the analysis that we are going to discuss subsequently will assume that we have a file that contains the data of position, velocities, forces, torques for all the particles at some equal interval of time. And these interval of time can be some integral multiples of the time that delta t that is used for integrating the equations of motion. The first property we would like to measure is the radial distribution function. We have already looked at the definition and the physical meaning of radial distribution function. It is mathematically defined by either of these two equations, and what it means is it characterizes the local structure of the fluids. Okay. So, in a material, if I tag a particular molecule and then if I go radially outward at a particular distance r, this g of r will tell me how many number of neighbors are there at a given distance. So, it gives us information about what is the number of neighbors, what is the neighbor distance and local structure of the entire material. We can actually use RDF for various purposes. For example, we can identify different kinds of phases of matter because the G of R or the RDF is quite characteristically different for gases, liquids and solids. By looking at those patterns, we can identify which phases of the matter that it exists. For the molecular system, we can calculate site to site RDF. That means, if I have molecules like water, I can calculate many possible combinations of site to site. In other words, we can calculate the RDF between oxygen to oxygen, or between hydrogen and hydrogen, or between oxygen and hydrogen. So, these site-site RDF tells us about which molecules are in the neighborhood, what kind of interactions are dominating, and what is the local structure of a molecular arrangement, or what is the local arrangement of atoms within a molecular system. And we also saw that when we use potential truncation and we want to calculate the trail corrections, we saw how the GFR or the RDF can be used to calculate thermodynamic properties from which long range corrections can be calculated. This involves calculating the tail correction for the energy or the correction for the pressure, etc. And more importantly, if you take the Fourier transform of the RDF, it basically refers to the structure factor, which is experimentally measurable using scattering techniques. So, in that sense, this radial distribution function is one of the most important structural characterization one can think of, because it gives wealth of information about the phases, local arrangements, correction for long range truncations, and even to experimentally compare with experimental data. So, because of this importance, we will see how this mathematical definition of GFR that we have is actually calculated in an MD simulation. In other words, this mathematical definition depends is an ensemble average or a time average of delta functions. But how are we going to implement this in an MD code? So, to see this, we want to first take a look at this particular RDF, try to understand what it means, and then encode in the MD simulation the calculation. So, again we start with our the mathematical definition of GFR. So, it depends on the volume and the total number of particles in the system, and then we have to do this angular bracket here means it is either ensemble average or a time average. You can calculate RDF both from MD simulation and Monte Carlo simulations. When we do MD simulations, this angular bracket means time averaging. The same definition can be used for MC simulation also, but there this angular bracket would mean an ensemble average. So, now we can define rho is equal to n by v. This is the average density of the entire system, that is the total number of particles divided by the volume. So, if I use this definition, I can substitute n by v as rho and I take the rho to the left. So, I can write rho times GFR is nothing but 2 by n this quantity. And we also noted this RDF has certain property, that is if I integrate this rho GR over a distance of 0 to infinity, then this basically gives me the total number of neighbors in the simulation box, that is n minus 1. So, that means you are looking at, in a simulation box, you are looking at a target molecule and then you are actually averaging all the neighbors from 0 to infinity. So, that should give me all the other molecules in the system, which is n minus 1. When n is very large, you can even approximate this to n itself. So, we take this as a working definition for GFR, and from here we try to derive an expression that can be used in MD simulations. So, this integral we will take. So, we take this integral and write this for a small volume V in the limit of r to r plus dr. Okay. So, what this means is, so about a particle, we take a small volume at a distance r to r plus dr. So, we try to write this expression for a small volume V, that is the volume of this shell. So, this V at r comma del r basically means the volume of the shell at a distance of r to r plus dr. So, what we do here is we have rho and then we calculate GFR at r over a small volume. This is not delta V, it is just V, and that is this shell volume, and then we divide by this n minus 1, then that should give you the probability that an atomic center lies in a spherical shell of radius r and a thickness of dr with the cell centered on the another atom. So, basically it tells this fraction here tells me that what is the probability that an atomic center lies in a, so you are asking, suppose what is the probability that an atom here would be present at a distance of r from another particle with which this shell is centered. Okay. And so, we take this as a definition, and what we are going to do is now you take this in from here, you substitute for the GFR, and then this integral is actually taken inside the delta function, and then now we actually so we now write this integral over a small shell of thickness delta r. So then the left hand side can be written as sum over many shells of thickness delta r. So instead of doing a continuous integration from r 0 to infinity, we take finite thickness of delta r, and then we sum over all this. So basically we are writing a continuous integration into a sum of discretized spatial integration. So we have on the left hand side rho times sum over all the shell width of delta r g of r times v, and then the right hand side we have again this integral is now written in terms of sum over all possible shell thicknesses, and we can see we have interchanged the integration and summation, which is okay here, and then you have on the left hand side and right hand side. And if you look at this particular term, that is sum over the double sum I is equal to 1 to n and j greater than I to n delta of r minus rij times dr. So this is nothing but number of particles in a given shell of radius r to dr. Okay, this is basically number of particles, is basically counting operation in the shell of radius r to r plus dr. So we take this expression and substitute here. So from here on the left hand side we keep it as such, in the right hand side for this particular angular bracket we substitute the angular bracket of all the number of particles. Now if you compare these two, left side and right side, and you can actually match the terms within this summation, because both terms correspond to a sum over certain quantities over a small shell thickness of delta r. So then from here you see this rho times g times v is equal to 2 by n times the mean n, and from here you can write the g of r is given by 2 times the average number of particles at a distance of r to dr divided by number of particles, density and the volume. So we will take this as a definition that can be used in the MD simulations. So what we are trying to do is the original definition, mathematical definition from StatMech is written in terms of delta function. We replace that delta function into a counting operation, but this integration has to be done in a discrete manner, because in MD simulation we have discrete set of particles and space is also discretized. So we replace the original mathematical definition into a spatial region of finite thickness, and then we calculate the number of neighbors in those thicknesses and then we average. So we will take this as the working definition for the G of R in MD simulation. So if you look at this particular definition, the angular bracket here is basically a time average, and we can explicitly write the time average n as 1 by m. Let's say there are m number of data points as a function of time, and this will give you the average time average number of particles. So here k is the index for the time points. So what this basically means is you have stored the data at a different time points and we are averaging over time, and this m here is the total number of time points, and nk would be the number of particles in the shell at time t. So now we have got m number of data points, m number of time points, and then we average. So we calculate the total number by summing over all the times and then divide by the total number of time points. So this will give us the time average of number of particles in a given shell of radius r to r plus dr. So when we substitute this definition n from here in here from this expression, then we get the final expression. This mean n is written as sum over nk divided by m. Now the practical question about how small or how big the thickness of the shell should be is to be decided. So typically one would choose for a Lennard-Jones system, if sigma is our length scale, delta r can be about 2.5% of sigma or maybe 5% of sigma depending upon the density. And we also have to note that this g of r can only be calculated for r less than or equal to L by 2, because beyond that then your periodic images will be interfering. So the g of r can be only calculated from a distance 0 to L by 2. That's a maximum limit one can go. So next we will see how this expression that we have here is implemented in an MD code. So this is our definition. So there is a time averaging, and then there is a number averaging, and then there are some constant quantities like density and the volume, etc. So now this volume here, as I said before, is given by 4 pi 3 r plus dr cube minus r cube. So this is the volume that we need to calculate, and this density rho is a fixed density which basically tells the average density in the system. So, if you look at this particular diagram, this particular algorithm, the way it works is the information that we get in MD simulation is the pair distance and the square of the pair distance. And this distance, if you look at in a simulation box, and if you ask what is the range at which this simulation, the two particle can be separated from, so they can go from 0 to L by 2. So, that is a range by which the separation distance can be varying, but actually it is not exactly 0, it can actually go from 1 sigma. So, we will say 1 sigma to L by 2 sigma. So, this is a range. So, what we are going to do is we take we go to all the pairs, and then you find what is the distance between a pair which can fall anywhere in this range 1 to L by 2, and this entire space is going to be now discretized into equal width of delta r. Okay, so the spacing between, so this entire length scale of 0 to L by 2 is split into various bins of size delta r. So, whenever a pair of particle has a particular distance which falls here, then we basically account the number of particles in this particular bin. We increment the number of particles in that bin. And similarly, if you have taken another pair of particle, and if you see that that particular pair of particles distance falls somewhere here, then in this particular bin, we put those two particles in that particular bin. So, by doing this counting operation, we can make a histogram of what is the number of particles in each of this particular distance, and that is what is being done in this particular algorithm. So, we can see that there is a double loop, just like how we calculate forces. We sum over I equal to n minus 1 and then j going from I plus 1 to n, and then we calculate the Rij square, that is the square of the distance between particle I and j. Before we calculate this, we would have ensured potential truncation, minimum image convention, everything is taken care of. So, we have done all the steps and we have come to the calculation of Rij square. So, then we calculate the absolute value Rij by taking square root of this. So, this is the distance by which particle I and j are separated. So, now I want to know in which bin this particular distance Rij falls. To do that, I divide the Rij by delta r. So, delta r is the thickness of the width of the bins. So, when I divide Rij by delta r and then make the integer out of that, so that will give me index for the bin. So, this is a first bin, second bin, third bin, fourth bin, etc. So, based on the separation distance and the width of the bins, we can identify which index that particular bin will correspond to. So, this bin will be an integer, and it is an indication where that particular pair of particles will correspond to. Now, we can also define some maximum number of bins, because the maximum number of bins is also known, because we know the total length is this, and it is actually not mentioned here. The maximum bin will be nothing but L by 2 divided by delta t, sorry, delta r. So, that would be your maximum bin. Okay. And now what we do is we make a histogram. So, the histogram will keep counting the number of particles in that particular bin. So, corresponding to the bin index for this particular pair, we increment the particles by 2, because both I and j are in the same bin here, and then we do this over and over for all the pair. Okay. In summary, what we are trying to do is this, first we calculate pair distance between I and j, and this I and j loops over all the possible pairs. For a given I and j, we find what is the distance between those particles, and then we make a bins of size delta r, and then find out for the given separation distance Rij, which bin that distance correspond to by finding out a bin index. And in that particular bin, we add two particles, because there are pair of particles belonging to that particular distance. Now, the distance is actually mapped into a bin with an index. So, this is basically building a histogram of number of particles in a given distance. So, after we do this, this is done for one particular time, and we have said that we are storing this information after equilibration in many number of time points. So, this operation can be done over many time points also. So, we are actually summing over all the pairs for a given time, and we are actually repeating the entire process over many period of time, because we are looking at time average also. So, after the bins are accumulated, then what we are going to do is we will at the after summing over all the time points, we come out of the time loop, and then you do final correction by adding the extra terms or the constant terms. So now we are going to loop over all the bins. So like I said, if I know the bin index, I know what is the limits of what is the distance and what's the limits of those boundaries are. So now I'm going to sum over I'm going to loop over all the bins from 1 to some max bin, and then we want to, let me just write this again. So all these bins are of equal length, delta r. So this is index 1, 2, 3, 4, 5, 6, etc. It goes all the way to maximum bin, and each bin has a r lower and an r upper. Okay, so that basically gives a limit of the bins, the lower limit radius and upper limit radius, and similarly for the second and third and so on. So now what we are going to do is we are going to loop over all the bins 1, 2, 3, 4, 5, that is this, and then we find what is the lower limit of the r value for each bin from this operation, that is bin minus 1 times delta r. So I take this bin index, subtract 1 and multiply by delta r, and that will give me what is the range of these values. For example, when bin is equal to 1, so the RL will be 0. So that's a starting point. And when bin is equal to 2, so this will be delta R, and this will be 2 delta R, this is 3 delta R, 4 delta R, etc. So it goes all the way this. So this gives a physical length scale of the boundaries of the bins. Okay. The reason why we need this absolute values of this radius is because the volume depends on this lower limit and upper limit. Okay. So if I want to know what is the volume of this particular bin, I need the lower R and upper values of the R, because I have to find the total volume. So you can see that R lower is obtained by looking at the bin index. R upper is basically calculated by adding R lower to delta R, because the width is always delta R. So then we calculate the volume here, and the volume is nothing but 4 by 3 rho by. So we can see that this is a constant, so we are doing it outside the loop, and only this particular quantity will depend on the bin size. So that is what done here. You can see this is R plus delta R cube, that is R upper cube minus R lower cube. So this entire thing that you see here is this particular expression, and it has to be multiplied by a factor of 4 by 3, and then rho also is taken into account. Okay, because anyway we are going to do rho times b. So if I do rho here, then there is going to be a factor of rho here, and all those constant values like 4 pi rho by 3 are calculated as a constant, and this variable is then multiplied with this rest of the term. So this n ideal here is basically nothing but rho times v. Then we calculate g of r corresponding to each of those bin from this formula. So you can see that we take this n and then divide by the total number of time step, that is m, and then divide by the n, that is here, and this n ideal is nothing but the rho times delta v. We don't have to do this 2 here because we already added 2 particles every time we counted in this operation. So when you do this, what we can get out of this is we will get an array where bin index versus g of bin will be given. So this bin index goes as 1, 2, 3, 4, etc. as an integer, and then the corresponding values of g will be calculated. But what we need to do also is we need to plot g of r as a function of radius. So it goes something like this. Okay, whereas we don't have r value, but we have only bin's index. But we already know, if I know the bin index, I know what is the distance that it should correspond to. So we take for each of this bin, we find r as r lower plus delta r by 2. That is, basically we are fixing the g of r value at the midpoint of each bin, and this midpoint is nothing but RL of that particular point plus half of delta r. So then if I transform this bin index to this r, then I can make values of r versus g of r, and I can plot this. Okay, so that is another step that we can store. After this loop is done, we can generate an array of r values corresponding to the bin index, and we already know what is the g value in those cases. From here we can calculate g of r. The next function we would like to calculate is a time correlation function, and you might recall that the time correlation function is defined as, again, a time average or ensemble average of some property A at time some t naught, the same property multiplied by with itself, but at another time point t plus t naught. So this t here is called the delay time. That is, we are looking at the same property separated by some delay time. So, if you look at C of 0, it means simply a square, which means you are looking at the same variable at the same time. So, you can becomes simply a square. Whereas, if you correlate the same variable at time t and another time t plus t naught, then we are talking about correlation after a particular time t. So, this t here we will use as a delay time, and this t naught here basically means this comparison can be done over many initial conditions. So, we have already noted that this time correlation function has relevance to transport property definitions. That means, if I can calculate time correlation functions, we can calculate certain transport properties. For example, the viscosity is related to the time correlation of velocities, and if you calculate stress autocorrelation function, the system's viscosity can be calculated, etc. And so, we already noted some Crete-Gubo and Einstein relations where the time correlation functions are related to those transport properties. So, we know the importance and significance of time correlation functions, and let us see how to calculate this in MD simulations. There are actually two approaches in dealing with time correlation functions. The first one is a direct approach, which is very easy to code, and the other one is a fast Fourier transform approach. And in this lecture, we will talk about only the direct approach. The fast Fourier transform approach is quite efficient, especially if you have very long time correlations, whereas a direct approach is something simple to calculate, and as long as you have a very short times correlation or short response times, you can use direct approach itself. Now, before we do how this time correlation functions are calculated, we have to understand how the data is stored in the file, in the production run. So, you can see this, the first arrow basically shows a time arrow. So, this is your, this t equal to 0 is actually not the initial time. Prior to this, we would have done initialization, equilibration, everything is done, and from after that we reset the time. So, when we try to calculate properties in MD simulation, we reset the time in the production run, and this t equal to 0 is not the initial condition, but after the equilibration is done, the time is reset at 0. And then we would have integrated the equation of motion at delta t, 2 delta t, 3 delta t, etc., etc. In each of these time points, we would have information of Ri, Vi, Fi, etc. So, that is what the equation of motion will give us. So, all these things we can store. But even though the computer actually simulates the system as a function of equal interval of time, but for the property calculation, we do not have to store all these values, but we can store values once in a certain number of time steps. In this particular example, the data is stored in a file after every third time point. Okay, so this is at t equal to 0, then we store the data at 3 dt, then 6 dt, then 9 dt and 12 dt, etc. We could, instead of 3, we could have chosen 5 or 10 also. Okay, that is the interval at which we are storing the microscopic data in a file. For this illustrative case, we have taken that this delta t here is basically 3 times dt. Okay, once in every 3 time step we store the data, so that we don't have to bookkeep a large number of data. Now, this time, real time, is now we write in terms of some index. The first data point we say is 0. This this is a 0th time 0th data set, first time data set, second and third and fourth. So, we are basically replacing the time information into some label 1, 2, 3, 4, 5, etc. And then we can easily see that if I know the label of this data, I know what is the absolute time it corresponds to by simply multiplying tau times dt, delta t. Okay, suppose this basically means 1 delta t, that is basically 3 dt. Okay, so this data point basically is this. Similarly, when tau equal to 2, this would correspond to 2 delta t, which is nothing but 6 dt, and this corresponds to this. So, all we are trying to do is that we are eliminating the time information and putting it into some simple labeling. Okay, this basically tells the first data set, second, third and fourth, etc. And we access these data set from a label tau, and we know that once the tau is known, we can find what is the actual time each of these data set corresponds to. Okay, so this must be clear first, because when we actually look at an MD code for calculating autocorrelation function, we are not going to work with this time directly, but we are going to look at this kind of index label of the label for the data set that we have here. So, then the calculation of time correlation function comes from this mathematical definition, but this ensemble average, as I said, is basically a average over many initial conditions. So here the variable A is autocorrelated. So we take the value of A at some initial condition tau naught, and then I look at the same variable A with a delay of time tau. Okay. So then I multiply this, and then I average over many such initial conditions of tau naught, and the tau naught can go from first to some tau max. This tau max here is the number of initial conditions with which this is averaged over. Again, we note that this initial condition does not mean the initial condition of the MD simulation. This is we have taken care of the equilibration. We know that the system is at equilibrium, and after that we are doing this. So now the data set that I showed, I said that can be labeled as tau, and then we have this data 0, 1, 2, 3, 4, 5. So these are the label at which we know the microscopic data, and this C of tau is to be calculated over many correlation times. So now if you look at this there are various possibilities by which we can calculate this correlation functions here. The first thing is, if you take this data and this data, they are basically delayed by a 1 tau unit. Okay, so we call that as a C1. Okay, so I can take A0, multiply with A1, then I'll get a correlation with the delay time of 1 tau. And I can also take these two data set, and these two data set also delayed by 1 tau. So I can take A1 and A2, take product of them. So that will give me also correlation function with the delay time of 1 tau. Similarly, I can take 2 and 3 also, and these two data set also separated by 1 tau, and consequently I can take A3, A4 and A4, A5 also. So you can see all these pair of sets A0, A1, A1, A2, A3, A4 and A4, A5, all of them basically correspond to exactly the same delay time of 1 tau. So you can see how many number of pairs are there. In this case, there are 5 number of pairs, and this is what I was talking about as a tau max. So now for calculating C of 1, I can take 5 set of data and then average over those 5 set of data. So that gives me the calculation of C1. So here we are taking some finite set, but the actual data set would be very long. So you'll have very many number of tau max of the order of thousands. Now let's get to the second possibility, that is, we'll now look at correlation function with a delay time of 2 tau. So then I can take the data 0 and 2, these two are delayed by 2 tau, and then I can take 1 and 3, these two are also separated by a delay time of 2 tau, and then I can take 2 and 4, these are also delayed by 2 tau, and then 3 and 5, and I cannot take 4 onwards because I don't have 6 data here. So because of that, the tau max for delay time of 2 has only 4 contributions because we don't have A6. So we can take A0, A2, A1, A3, A2, A4, A3, A5 and nothing beyond because we don't have A6. So this gives us only 4 different possibilities. So now this autocorrelation function at tau equal to 2 can be averaged over only 4 initial conditions. And now we can go to A3, tau 3. So again, in this example, if I want to look at correlation function with the delay time of 3, then I can choose A0, A3, A1, A4 and A2, A5. That gives me only some 3 contributions. If we go to A4, consequently, you will see that A0, A4, A1, A5, only 2 contributions. For correlation function with a delay time of 5 tau has only one data set, that is 0 to 5. So as you can see that longer the correlation that you want to calculate, lesser the amount of data that you have to average from. So that's why if you look at the correlation function, you will get a very smooth data for a very short times. As you go to longer and longer delay times, you get a lot of noise because of this very less number of samples to average from. So in a computer code, we basically take this, we read this data set and then look at all possible ways in which we can combine the data to get correlation times with fixed delay times by calculating C1, C2, C3, C4, C5. So once you calculate in this case, you will have a data C of tau, where tau is equal to 1, 2, 3, 4, 5. So you'll get a data something like this. Okay, the data are very highly correlated at a short delay time. As you go to longer and longer delay time, you can see that the correlation time will decay. Okay, that means the memory of the system is gone if you go to longer and longer delay time. Whereas when you are looking at the data at very close time intervals or close delay times, they are highly correlated. Okay, so this is a typical way in which this correlation function will decay. So now let's see how this is implemented in the MD code. So we want to take this as the definition of the time correlation function. The first thing is to kind of initialize the autocorrelation function, because this is a sum operation. So we are going to keep adding terms over and over. So we initialize them. This norm t here is basically the tau max, how many number of times that we add from a given set of data. So if you look at this, we define there are two variables. We call this as t core. So this t core is nothing but the maximum correlation time that we want to calculate. So you can see in this particular data set, we can calculate up to maximum of tau is equal to 5, because you can take the first data and the last data, they are basically separated by the maximum tau, which is 5 here. So tau core here is basically the maximum tau that we can calculate, and tau run is basically the maximum number of data points. In our case, we have about 5 data points, so that is also 5 here in both cases. In many times, we will have many data points, but a very short, we might want to calculate only a small correlation times. What this basically means is, if I look at the file in which data is stored, I might have data all the way up to some 100 values. Okay, this is a tau is equal to 0, tau is equal to 1, etc. So I showed only 5 in the previous slide, but you may have a very long trajectory, and then you may have stored a long set of data. But the correlation time need not be all the way from 100. You can say that I want to calculate correlation time only at maximum correlation time should be 10 only. Okay, so this number tau max or tau core can be smaller than or equal to the total number of simulation steps. So that's the initialization that we do first. And then if you look at this loop, what it does is, so we first have a index for the data set t naught, starts at 1 and goes all the way to t run. So remember, t run is the total number of time points, that total number of data sets that we have, and then we take the value of a at the first time point, and then we go to the another loop in which the starting time is t naught itself, and then it goes to some maximum number of data sets that you have, and then it calculates the delay time tau, which is t0 minus t naught, and then we calculate this autocorrelation function by taking a0 and multiplying with the a, which is at a delay time of tt0. Okay, and then this is getting added up, and then how many times we do this averaging is coded in the norm t. The way you can actually look at this algorithm is, you substitute t0 equal to 1 and then t20 equal to 1, and then look at what kind of data that we are going to sum up. So if you expand this algorithm, what you will see is that we will be starting at this point, and then we will do summing over this. So we will calculate C1 using these two, and then C2 also will get using this. So we go we go basically column wise in the algorithm like this, because first we will take A0 value, first correlate with 1, then correlate with 2, then correlate with 3 and correlate with 4, etc. That means we are actually summing over these pairs. Then this counter is moved to 1, then we do 1 2 1 1 2 1 3 1 4 1 5. That means we are going through this way. Then we move the counter to A2, and here we are going to do 2 3 2 4 and 2 5. That is, we are going vertically down, and then by this we can accumulate the correlation function for all the possible tau values, and after that we normalize by the tau max, which is the total number of times that we have summed over, and we can plot C of t as a function of time after this. So with this, in this lecture we showed the numerical implementation of calculating RDF and the direct method of calculating autocorrelation functions. There are other methods to calculate autocorrelation functions, such as fast Fourier method, but that is something that we have left here. So you should look at the working principle of this particular time correlation function to fully understand how this algorithm works.